I should say with a factor of 2. 1/2 of this length is the rate at which area is swept. How do we see that? Well, let's take a small time interval delta t. In time delta t, our planet moves by v delta t. Okay? So if it moves by v delta t, it means that this triangle up there has two sides. One is the position vector r, the other one is v delta t. So its area is given by 1/2 of the magnitude of the cross product. That's the formula we've seen for the area of a triangle in space. So the area is 1/2 of the cross product r and v delta t, magnitude of the cross product. So to say that the rate at which area is swept is constant means that these two are proportional. Area divided by delta t is constant over time, and so this is constant. Okay. Now, what about the other half of the law? Well, it says that the motion is in a plane, and so, we have a plane in which the motion takes place, and it contains also the sun, and it contains the trajectory. So let's think about that plane. Well, I claim that the position vector is in the plane. Okay, that's what we are saying. But there's another vector that I know is in the plane. Well, you could say, okay, the position vector at another time, or at any time. But in fact, what's also true is that the velocity vector is in the plane. Okay, if I'm moving in the plane, then position and velocity are in there. So the plane of motion contains r and v. So what's the direction of the cross product r cross v? Well, it's the direction that's perpendicular to this plane. So it's normal to the plane of motion. And that means now that actually we've put the two statements in there into a single form, because we are saying r cross v has constant length and constant direction. In fact, in general, maybe I should say something about this. So if you just look at the position vector and the velocity vector for any motion at any given time, then together they determine some plane. And that's the plane that contains the origin, the point, and the velocity vector. If you want, it's the plane in which the motion seems to be going at the given time. Now, of course, if your motion is not in a plane, then that plane will change. It's somehow the instant, the plane in which the motion is taking place at the given time. And to say that the motion actually stays in that plane forever means that this guy will not change direction. Okay, so so Kepler's second law is actually equivalent to saying that r cross v equals constant, equals a constant vector. Okay? That's what the law says. So in terms of derivatives, it means d by dt of r cross v is the zero vector. Okay? Now, so there's an interesting thing to know, which is that we can use the usual product rule for derivatives with vector expressions, with dot products or cross products. There's only one catch, which is that when we differentiate a cross product, we have to be careful that the guy on the left stays on the left, the guy on the right stays on the right. Okay, so if you know uv prime equals u prime v plus uv prime, then you're safe. If you know it as u prime v plus v prime u, then you're not safe. Okay, so that's the only thing to watch for. So product rule is okay for taking the derivative of a dot product. There you don't actually even need to be very careful about the order of things, or derivative of a cross product. There you just need to be a little bit more careful. Okay, so now that we know that, we can write this as dr dt cross v plus r cross dv dt. Okay? Well, let's reformulate things slightly. So dr dt already has a name, in fact. That's v. Okay? That's what we call the velocity vector. So this is v cross v plus r cross, what is dv dt? That's the acceleration, a, equals 0. Okay, so now what's the next step? Well, we know what v cross v is, because remember, a vector across itself is always 0. Okay, so this is the same as r cross a equals 0, and that's the same as saying that, you know, the cross product of two vectors is 0 exactly when the parallelogram that they form has no area. And the way in which that happens is if they're actually parallel to each other. So that means the acceleration is parallel to the position. Okay? So in fact, what Kepler's second law says is that the acceleration is parallel to the position vector. And since we know that acceleration is caused by a force, that's equivalent to the fact that the gravitational force is parallel to the position vector. That means, well, you know, if you have the sun here at the origin, and if you have your planet, well, the gravitational force caused by the sun should go along this line. In fact, the law doesn't even say whether it's going towards the sun or away from the sun. Well, what we know now is that, of course, the attraction is towards the sun. But Kepler's law would also be true, actually, if things were going away. So in particular, say, electric force also has this property of being towards the central charge. So actually, if you look at motion of charged particles in an electric field caused by a point charged particle, it also satisfies Kepler's law, satisfies the same law. Okay, that's the end for today. Thanks.